Hello friends, I am Dr. Nitin Naik from the Department of Structural Engineering, Sanjani College of Engineering, Koparwa. Friends, we are starting our discussion on theory of elasticity and plasticity. So we will start with the fundamentals or the introduction of the subject. We will start with definition of stress. What is meant by stress? When a bar of uniform cross section is subjected to a tensile force along the axis of the bar. So here in this figure, force P is acting along the axis of the bar. Then the average stress induced across any transverse section perpendicular to the axis of the bar and away from the region of loading is given by P upon A. So normally we are using letter sigma to indicate stress. So sigma is equal to P upon A. This formula we are using in strength of materials. So here these are the three figures, and this three figure shows stress variation at different sections. So this is stress variation at section AA. So this is section AA. This is stress variation at section BB. So this is section BB, and this is the stress variation at section CC. So this is section CC, which is away from the point of application of the load. Now this section CC is taken at a distance D from the point of application of load or region of loading, where D stands for width of the bar or depth of the section or depth of the bar. And at this section the stress developed is equal to P upon A. This formula we are normally using to calculate the stress, and this formula is according to the Saint Venant principle. So let us see what is Saint Venant principle. Saint Venant principle. Saint Venant, a French engineer and mathematician, observed that near loads, high localized stresses may occur. So here in this figure, the section is considered very close to the point of application of load, and here through the distribution, you can observe the localized high stresses. Okay. Further, uh, but away from the load at a distance equal to width or depth of the member. The localized effect disappears and the value of the stress can be determined from an elementary formula sigma is equal to P upon A. So here if we move further away from the point of application of load, we will have stress distribution like this. So here the effect of localized stresses is somewhat reduced. Further, if we move away from the point of application of load at a distance equal to D, where D is width of the section. Now here we will have uniform stress distribution, and here stress is equal to force upon the cross-sectional area of the member on which load is acting. So this is called as Saint Venant principle. Now in this subject, we shall deal with the mechanics of deformable solids. Remember, at entry level of engineering, we are studying mechanics of rigid bodies, and we call it as engineering mechanics or applied mechanics. In engineering mechanics or in applied mechanics, we are assuming that the body is rigid, means we are ignoring the deformations because of the external loads which are acting on the body. But here in strength of materials or in theory of elasticity, we will consider the deformation, effect of deformation. And hence, this is mechanics of deformable bodies. The beginning of the subject may be either from the analysis of strain, analysis of strain, or analysis of stress. In theory of elasticity, we usually starts with analysis of strain. We usually starts with analysis of strain, and the analysis of strain consists of geometry of deformation without considering the forces that causes the deformation. While in elementary strength of materials, we are usually start with stress. Please recall the first chapter of strength of material, stress and strain. So we are usually starting with stress in elementary strength of materials, but in theory of elasticity, we starts with analysis of strain considering the geometry of deformation and without considering the forces which are responsible for the deformation. So this is the difference between strength of materials and theory of elasticity. Now let us discuss few important terms which we will come across the subject. First one is continuous medium. What is mean by continuous medium, and hence what is mean by continuum mechanics? When a matter is continuously distributed, means without having voids in it, then it is called as continuous medium. And the mechanics of such a body or bodies is called as continuum mechanics. Then body forces. Now to consider the body forces and the surface forces, we will go through this figure. In this figure, a body is placed with reference to three reference axes x, y and z. Okay, this is origin of the reference system, and this is the object. This object is resting or supported by three supports r1, r2 and r3. So there are three supports r1, r2 and r3. So as we know, when a body is supported by supports, the supports offer reactions. So here this support will offer reaction R1, R2 and R3. So these are the reactions R1, R2 and R3. These are the surface forces. Let us see what is meant by body forces and surface forces. Body forces, the forces act on each volume, each volume element of a body are called as body forces. For example, weight of a body. Weight of a body is a body force which acts through the CG of the body. Inertia force F is equal to m into a, where m into a is called as inertia force, and magnetic force. These are the body forces. While the surface forces are the forces which act on the surface or area element of the body are called surface forces. The forces which act on surface or area element of the body are called surface forces. Now here, this is the surface, and on this surface forces F1, F2, F3 are acting. So F1, F2, F3 are the surface forces. Similarly, R1, R2 and R3, these are the surface forces. Okay, let us consider one more example. Let us consider a brick element. Again, we will consider that element. See, let us imagine an element, brick element, like this. Okay, now this is force F1. This force is acting on the area or area element or surface. Hence it is called as surface force. Let F1 be the first surface force. Now the second force is like this, F2. This is again a surface force. Okay. Here if suppose the force is acting F3, this is again a surface force. If this brick is supported by the supports, then the reactions are nothing but the surface forces. Now what is meant by distributed forces? When the area lies on the actual boundary of the body, the surface force distribution is called as surface traction. Surface traction means force per unit length. It is somewhat like UDL, force per unit length. Now let us consider this edge, and if on this edge force is acting like this, see the force. Magnitude is, let P be the magnitude. So P per unit length is called as surface traction. This force is acting on the actual boundary of the brick element. Hence it is called as surface traction. Okay, or distributed force. Similarly, stress at a point can be studied like this. Let us consider a plane. bounded by x1 and x2, and let x3 be the third axis which is perpendicular to the plane. Okay. Now we know that through a point, number of planes we can draw. Through a point we can draw number of planes. Let us consider a point. Okay, through this point I can draw a vertical plane like this, a horizontal plane can be drawn, an inclined plane can be drawn through the same point with different orientation. So through a point number of such planes can be drawn. So here the sentence is, since an infinite number of planes can be drawn through a point, thus there will be an infinite number of stress vectors acting at a given point. So stress vector, one stress vector may be there acting along this plane, second may be acting along this plane, third may be acting along this plane, like that. Okay. Each stress vector characterized by the corresponding plane on which it is acting. Okay. The totality of all stress vectors acting on every possible plane passing through the point is defined to be state of stress at a point. The totality of all stress vectors acting on every possible plane through the point is defined to be the state of stress at a point. Now, if you consider the resultant of all the stresses acting on these planes, and if you consider a single stress, then that is the total stress or state of stress at a point. Now, there may be different stresses acting on different planes, and these stresses may have different values, but from the designer's point of view, the stress which is critical is very important. So this critical stress we have to calculate, and this critical stress is very important for a designer. For example, now on this plane, let us follow the cursor. Stress is applied. This red color stress is applied. This stress can be resolved into a stress acting along x1 axis, acting parallel to x1 axis. Similarly, acting parallel to x2 axis and along or parallel to x3 axis. Okay. So this stress is called as normal stress because it is normal to the plane, and the remaining two stress components are called as shear stresses. Thus, a stress may have three components like this: normal and two shear components. Now, let us discuss in detail what is normal and shear stress components. Let Tn be the stress vector at point P. So here this is point P, this is point P, and this is the stress vector acting at point P, Tn. Okay, whose outward drawn normal is n. Now if I draw normal to this plane, this is the normal. You can observe a black arrowhead there. Here this is the black arrowhead, and this is normal to the plane. Okay, and denoted by n, denoted by n. The component parallel to n means normal is called as normal stress and is denoted by sigma n. Now component of this Tn stress vector along the normal is called as normal component sigma n. The component perpendicular to this normal, now this is the normal to the surface and this is perpendicular drawn to this normal, and the component of this Tn perpendicular to the normal is known as tangential stress or shear stress and is denoted by Tn, and thus we can write the stress vector Tn square is equal to sigma n square plus tau n square. We have already studied it in engineering mechanics. If suppose this is tau n, this is sigma n, then according to Triangle's law, the resultant is a closing line, and this is nothing but the stress vector acting at point P, Tn is equal to sigma n square plus tau n square. Okay. Similarly, the given stress vector can be resolved along three axes x, y and z that we will discuss in this figure. Now suppose this is point P, this is point P and this is x axis through point P, this is y axis through point P, and here this is z axis, and hence Txn, this is Txn, is component of stress vector Tn along x axis. Similarly, Tyn is component of stress vector, this is Tyn, along y axis, and Tzn is component of stress vector Tn along the z axis. And again, using the same concept, we can write Tn square is equal to Txn square plus Tyn square plus Tzn square. So this is about the components, normal and shear stress component as well as components along the three axes. Now let us consider rectangular components of stress. Now consider an object placed in a space. These are the three reference axes x, y and z. Okay. Now we will take a cut. We will consider a cut. For example, cut can be like this, parallel to x axis. Okay, now here in figure, this figure is having a cut. Let the body shown in figure be cut by a plane parallel to YZ plane. Now we will cut this body with the help of a plane which is parallel to YZ plane. Which is the YZ plane? The plane bounded by Y and Z axis is called as YZ plane. Follow the cursor, this is YZ plane. And the body is cut by a plane parallel to YZ plane. The normal to this plane is parallel to x axis. The normal to this plane is parallel to x axis. This is the normal. This normal is parallel to x axis. Hence, this plane, please follow the cursor, this plane is called as x plane, right? Thus, we can define the plane as x, y and z. If the normal drawn to the plane is parallel to y axis, then that plane can be called as y plane. If the normal to the plane is parallel to z axis, then that plane is called as z plane. Okay. Let Tx be the resultant stress vector. So this is the resultant stress vector acting at point P on x plane. This is x plane, remember. This resultant vector can be resolved into three components along x, y and z axis. Okay. So if you resolve this Tx along this normal which is parallel to x axis, then it is called as component parallel to x axis and normal to the plane sigma x. Tau xy means component parallel to y axis. It is also called as shear stress since it is acting in the plane. Tau xz is component parallel to z axis, also called as shear stress. Now here the subscript xy, this is xy, xz, what it indicate? The first letter indicates the plane on which the stress is acting. So both these stresses are acting on x plane. Hence the first subscript is x. While the second indicates the direction of the component. So tau xy, the second subscript is y. It means that this stress is acting in y direction. See, this is the stress tau xy acting on x plane in y direction, acting on x plane in z direction. So in this way, rectangular components of a stress can be studied. Thus, at any point P, one can draw three mutually perpendicular planes x, y and z, right? So let us consider this figure again to the right of the board. We are having now three planes. This is x plane, which because the if you draw normal to this plane, it will be parallel to x axis. Please follow the cursor. This is y plane, because if you draw normal to this plane, it will be parallel to y axis. And this is called as z plane, because if you draw normal to this plane, it will be parallel to z axis. Okay, so on x plane, what are the stress components acting? First is sigma x, second is tau xy, third is tau xz. See, the first subscript is x, so these two components are acting in x plane. Second is showing the direction, tau xy acting in y direction, tau xz acting in z direction. Similarly, on y plane there are three components, sigma y, tau yx and tau yz. Similarly, on z plane there are three components, sigma z, this is sigma z, tau zx and tau zy. Thus, there are 9 components. Stress at a point can be defined by its 9 components acting on 3 faces which are mutually perpendicular to each other. Now here the horizontal line, it shows the plane on which the components are acting. Sigma x, tau xy, tau xz, tau yx, sigma y, tau yz, like that. While the second this column shows the direction in which the stresses are acting. Stresses are acting in x direction, in y direction, in z direction. So this is all about the 9 components of stresses. Thank you.